Hey, Samaya. Let's start at 11:05, right? And to begin with, I'll say, well, I'll just draw this for a second. Hey, Esther. We're gonna come back at 11:05, but if you want, you can go ahead and draw what's on the board, right? While we wait, feel free to copy what is on the board. It should take up the whole page of your notes. Hello, Justin. Hello, Vicky. Hey, Josephine. We'll be back in 3 minutes, all right? Okay, it is time. Hold on, I gotta go get my tea. Good morning, John. Good morning, Allie. Is Ethan there? Good morning, Kevin. Nice to see you on time. Good morning, Shelly. Hopefully all of you who have been saying good morning to me. Good morning, Ethan. Have already drawn this on the board. Okay? So it should take up a whole page. And this is what we're gonna do. This is a super important lesson, but it's also pretty fast. All right. So we should just be in and out. We're gonna derive this formula, understand some of the intricacies behind it, learn like how to apply it, and then we're out. Okay? Hey, Siddharth. All right. So for those of us just joining us, I'd like you to please go ahead and copy all this on the board. What have I drawn? Okay. Let me tell you. All right. Hey, Alon. Here's what's really happening. I have my hand on a rope here, and I just shake it back and forth at a constant frequency. Okay? So I generate the wave, and then it travels to the right. Okay? So what I'm really interested in is this crest over here. All right? So here's the crest. Here's the crest. Now, am I saying this molecule on the rope is going to be here at a later time and here at a later time? No, right? This single molecule only goes up and down. That's what we went over yesterday and the previous day. So when I'm saying this crest is moving, I'm just talking about the actual energy, right? That packet of energy contained in the wave. How is it moving, all right? So what is time 1? If this is 0 seconds, how much time has elapsed here where I see a complete cycle of a wave? Oh, that's 1 period. I don't know what it is. Maybe my period is 1 second. That's what that looks like. Maybe my period is half a second. That's what that looks like. Maybe my period is 2 seconds. Right? Like that's, whoa, boom, 2 seconds, and then there I am, right? Good morning, Lars. I don't know, right? But so maybe the period is 2 seconds. I don't really care, right? Let's just say it took 2 seconds though. For this example, all right, let's say my period is 2 seconds. So this is actually 2 seconds. So what is this then? Compared to this, it's 2 seconds later, right? So this is 2 seconds later after this. What would this be then? How much time has elapsed from this initial starting point to where I see 2 crests and 2 troughs? What would the clock read at t equals 2? Let me see it in the chat, please. Good morning, Taz. If you're just joining us, Lars, Taz, Alon, I need you to copy all this down. It should take a whole page, but I've already asked the question. It should have taken 4 seconds, exactly, right? Why is it 4 seconds? Because it's 2 periods, right? Why do I know 2 periods have completely passed by? Because I see 2 whole sections, 2 cycles of waves, right? John is generalizing and saying 2t, great, right? And then T3 would be what? T3 would be what, right? How many seconds have passed there? 6 seconds, right? Or 3 periods. Cool, all right? I want to now look at the interval between T1 and T2. That's more interesting to me, all right? Because today we're going to be talking about the speed of a wave, okay? So what kind of questions would this answer? Let's see. Let's say at the Marianas, the Pacific Plate fault line, if there is a movement, how long will it take for the tsunami to reach the shore of Hawaii, Japan, Indonesia, Australia, right? To know that, I need to know where the wave originated, how far that point is from Hawaii to Japan to Indonesia to Malaysia to Australia to New Zealand, and I need to know how fast the wave is, right? So now we actually are going to find an equation that helps describe the speed or velocity of a wave, the propagation velocity of a wave, right? And to do so, all I have to talk about is how far did that crest travel? I don't know the actual number in meters, okay? But in terms of my anatomy of the wave, how far has it traveled? One wavelength, right? Can't you see that if my first crest started there and it ended here, in one period it traveled one wavelength. So my speed, right? My average speed from T1 to T2, right, is equal to one wavelength over one period, right? Let's say, I don't know, that looks around 10 centimeters to me, right? So this is equal to 0.1 over 2. So how fast is this really going? If my period is 2 seconds, it is 0.05 meters per second. 5 centimeters a second. That kind of makes sense, right? If it took 2 seconds to go from here to here, that looks like 5 centimeters per second to me, right? And what does this really look like? A period of 2 seconds looks like this. So imagine I'm generating these waves just by doing this. And that's what's making the rope go up and down. You can kind of visualize how quickly these are going to go, right? And what we've actually just derived is the wave equation, or the equation for propagation speed of a wave. So the propagation speed of a wave is one wavelength over the period. But since period is equal to 1 over the frequency, I can also write, but this is equal to lambda times frequency. So there's two ways to talk about the wave speed, right? You can either talk about it like this, or you can talk about it like this. Either one of those is equal to the wavelength, okay? So if I also remember, one key point, I'm going to go over two examples, all right? And the first example is really basic, okay? And let's say the speed of a wave in water, right, is around okay, let's say I dip my finger in a pool at 3 hertz, right? So what does that mean? I dip my finger there or my hand on a water surface 3 times per second. So that goes like dot 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 no dot 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 dot, right? So from a bird's eye view, that means 3 of these crests are generated every second, right? So if this is my finger, okay, all right, and this is the water surface. After 1 second, it looks like this. Right? Because all these crests are just radiating outwards. Does that make sense? 3 times per second. And after 2 seconds, it looks like there's going to be 6 of them, right? After 2 seconds, it looks like that, right? And they're still all going this way, right? Now, from a bird's eye view, if I'm in a drone and let's say I measure this distance to be around 2, no, it's probably closer to 8 centimeters. This is like 8 centimeters. I want to know, hey, what's the speed of this wave in water, all right? Well, let me go over my givens, right? My givens are very simple, right? The wavelength is 0.808 meters, right? Because I've already measured this to be 8 centimeters. So this is 8 centimeters. That's a crest to a crest. That's my wavelength. Oh, sorry. I got to check my hallway. There's a weird smell. So sick of this. My neighbors a floor below me always have their apartment door completely open. And it's cool, you know, it's cool, but, you know, and they cook a lot. And I always smell what they're cooking. And even if it smells good, sometimes I just want my apartment to smell like my apartment. I'm sorry. Okay, so let's keep going. The period, what is the period? I don't know, but the frequency is 3 hertz, right? So what is the period then? Oh, it's 0.333 seconds. Does that kind of, I hope that makes sense, right? Like, if I do 3 every second, each individual cycle takes 1/3 of a second to produce. So my period is 1/3 seconds, okay? And yeah, so either way, right, my speed is either 0.08 times 3 or 0.08 over 0.33. Either formula works, and they both tell you that it's 0.24 meters per second. Isabel, where would I find a candle that smells like me? Oh, my earwax. Genius. Okay. The way the drafts work in my apartment dictates wind always blows in from my door. It will never blow out due to the pressure differential, which is really annoying, right? Like now that means I really can't do anything about it. Because the air pressure in my room is always higher than the hallway. So air always goes from the hallway into my apartment. It's okay. We'll figure it out somehow. All right, so water, the speed of water in this example is 0.24 meters per second. Here's where we're going to change examples and go to example 2. Okay? If you remember from our lecture Monday and Tuesday, okay, I know the speed of a wave only depends on the material in water. So no matter how I dip my finger, if I speed it up, if I slow it down, if I make huge splashes, the waves are going to travel at the same speed. Okay. Hi, Ishraq. Can anyone please confirm whether or not Ishraq is a student at Bronx Science? Because if not, we're going to have to ban them. Okay. So you can try this, right? Next time you're at a beach, okay, you can like a lake like in Central Park where the ducks are, you can dip your finger and make like really cute ripples, and you can have like your friend like boom, like really splash it down. Boom. Right? And you'll see that your first crest and your friend's first crest will travel at the same speed. Like it only depends on the water. And because you guys are in the same pool and the same lake, then your wave speeds are going to be the same. Now, if you're in a tank and like this is made of oil and this is made of water, then of course your wave speeds are going to be different, right? That's cool. I mean, I don't know. He could be a student or she could be a student. Like, I don't know. And if they were a student, it'd be fine for them to stay. I just needed someone to confirm if they were a student. All right. So let's stay focused though. All right. So if this was oil and this was water, then they'd be different speeds. But if they're both the same water, the same temperature and whatever, right? Then the wave speeds are going to be the same. So now let's go over the example. What happens if I decrease my frequency? If my frequency decreases from 3 hertz to 1 hertz. So instead of going like bop, 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 bop to the water, all right, I just go bop, 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 right? If we look at our formula, V equals lambda times the frequency, someone with a poor understanding of physics would say, hey, if I decrease my frequency, then my velocity decreases. All right, if I go from 3 to 1, bop, 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 and I slow down the wave. Why is that wrong? That is not correct. If I decrease my frequency, my velocity will not change. My velocity won't change. Why will my velocity not change? When I'm at the pool and I go from da 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 and I go da da da, why does the velocity of my water wave, why is it unaffected? Everyone's talking about the length. I'm asking about the velocity. Why does the velocity not change? This is key. Because the material it's passing, the medium, is constant, right? Exactly. This only depends on the medium. This is only medium dependent. So it depends on the material it's made out of. Water, oil, liquid mercury. Yikes. It depends on the density of that material. It depends on the temperature of that material, right? And because I didn't change, and all I changed was my finger, right? The V is not going to change. Only because V is constant, I can say wavelength increases, right? No, because even like water, it depends on the depth of water, actually. And that can be our final example, actually. No, it won't. We're going to go over that next week, actually. So for water, the speed of a wave in water depends on the temperature, the density, how much salt is in it, and like barely, right? The salt barely affects it, and the depth. The depth really affects the speed of water. The deeper the water is, the faster the wave travels. Example 1 is accurate for a certain depth. I just didn't tell you the depth, okay? So the relationship between frequency and wavelength is only if my speed is constant. Remember that. Like if one increases, one decreases. If the other decreases, the other increases. That's only true if v is constant. Remember that, all right? Because v is lambda. So that's why, like, if I have a rope and I shake it and I increase my frequency, like that's why the wavelength decreases, right? That's why they become closer together, because the speed is constant. That's like the big thing, okay? With that, guess what? 27 minutes in, we're done, okay? If you have any more questions, I'd be happy to answer, just like Lars just asked and Alon just asked. And I'm really pumped to eat my lunch, all right, once we're done with this. So if there are no more questions, then get pumped because there's a short workshop I'm going to send out by probably noon. I'm going to do that right after we leave today. It's due tomorrow morning. We're going to go over the answers tomorrow morning. Chill pace. Well, Friday's chill. And then Monday, we're going to go over when velocity does change. So get excited about that, okay? Right. So look for it. I know we only have like 11 hours to do the homework, but consider this like classwork. Like remember in our when we were actually in school, like there was like a lecture and a discussion, and then we split into groups. That's kind of what this is, right? Except instead of like 20 minutes to do it, now you have 12 hours to do it. Okay. All right. Have a great day. Happy hump day. Happy Wednesday. All right. Thank you, Siddharth. We're all about getting pumped up. All right. I'll give you a song to get pumped up. This is can't find it. Wait. Oh, I think this is it. Hold on. I think this is. Hold up. I need to listen to this in headphones because if I play it on my speakers, then the stream will get flagged for copyright, and that's like horrible. Okay, no, this is it. This is it. Okay, cool. So I'm gonna link this song. Okay, get pumped up, and have a great day.